Now we calculate the pH of a weak base. Okay, not a strong base, it's weak. Here's 0.1 mole per liter Na2CO3. That's a weak base. It doesn't have hydroxide in it, so it's weak. Now, why is it a base kind of thing? Well, I don't see any H in it, so I know that it's not acidic. Now, you know, some things, of course, have H's in them and negative charges as well, and they can act amphoterically or amphiprotically to be an acid or a base. And on a chart, they'll be on both sides. How will you know which is which? Well, or whether or not a chemical reacts as an acid or a base. Well, just actually figure out if it's higher on the left or lower on the right. I guess that means then what you're looking for is whether a solution is more of an acid or a base by its position on a chart. But then, if you don't have those positions on a chart, how would you determine it? Now, I know I'm sidetracking a little bit from this question here, but this ion right here, bicarbonate, I just want to tell you, that is an acid in certain situations and a base in certain situations. But if you just put it into water, what is this chemical right here? That chemical right there, bicarbonate ion, because it's an acid that happens to be a pretty weak acid, kind of down here. But as a base, you would find it on a chart over here. So in the bases side here, where the strongest base is down here, hydroxide, and the weakest one, water, is here, and it's in the middle, that HCl3 negative, it's kind of a medium weak base. So in water itself, this chemical right here, HCl3 negative, would be more base than acid. Okay, just to illuminate something for you here. Now, okay, I digressed, but that was a little teaching point sort of thing. You're going to notice some amphoteric species later. You're going to have to determine whether they're acid or base. Figure out where their position is on the chart. Or you can calculate their Ka and their Kb. That's coming up in a second. But this chemical here is sodium carbonate. And sodium carbonate ion is a base. It's a weak base. It's kind of a strong weak base because hydroxide's down here and it says that I'm strong, everything else is weak, but carbonate says, well, I'm weak, but I'm kind of a strong weak. So now carbonate ion, that's in sodium carbonate. And look, take the metallic ion and get rid of it all the time when you're writing a net reaction. So carbonate is the active ingredient here, the sodium, goodbye. Carbonate, when it hits water, is going to do this. Takes a proton from water and turns into this bicarbonate, and the water turns into hydroxide. If you could calculate the concentration of the hydroxide in solution, you can find a pH. How are you going to do that? Well, first of all, you've added this to water and got the equation. Recognizing that the concentration of carbonate, when you dissociate this chemical, is going to be that concentration there, 0.1. One of these molecules makes one of these carbonates. Okay, so 0.100, icebox. So concentration, initial change is going to be lose X here to gain X here and gain X here. And by the way, if you're looking at this and saying, I don't remember this icebox stuff, you got to go to the equilibrium lessons to be able to remember how to do all of this. Because you got to do equilibrium chemistry first before you can calculate pHs of weak acids and weak bases. So there we got X's and X's. So 0.1 minus X, X and X. So the Kb, because that's the base, equals the hydroxide times the bicarbonate divided by that carbonate ion right there. But where do you get the Kb? Well, you have to be given that Kb. Or, on a chart, you look for the carbonate, and there's a Ka next to it, but that Ka belongs to bicarbonate. So, if you've got the Ka for bicarbonate, how can you find the Kb for this? You just divide it into the equilibrium constant for water, 1 times 10 to the negative 14. The relationship is this. If you take the Kw and if you take the Kb and you want to find the Kb, it equals the Kw over the Ka of the conjugate acid to that weak base. So here's the thing. If somebody gives you bicarbonate, this one right here, and it says, here's the Ka for that, what's the Kb for this? You divide that Ka into the Kw to get the Kb. On my chart, I have a Ka for carbonate here at 4.7 times 10 to the negative 11. And so that means the Kb for the bicarbonate is 1.00 times 10 to the negative 14 divided by the 4.7 times 10 to the negative 11. That's the Kb. And it's going to equal what? x squared over the concentration here, 0.10 minus x. Can you disregard that x when added to or subtracted from something? In the majority of these cases, you certainly can. So really, it's taking this number here times 0.1, take the square root of that, and what does that equal? X. But X is going to be the concentration of the hydroxide ion in solution. So the square root of all of this, okay, which is 1.00 times 10 to the negative 14 divided by 4.7 times 10 to the negative 11, all of that, and then times 0.10, you take the square root of that number there, and you're going to get the hydroxide ion concentration. How do you find the pH once you have the hydroxide ion concentration? You have to go 14 plus the log of that x right there, which is that right there. And if you go 14 plus the log of that number right there, you're going to get 11.65. What is that? That's the pH of a solution of sodium carbonate at 0.1 moles per liter. Looks like there's a lot of stuff to be able to go through here, and there is. But what you do is, you're just going to take the Kb times the concentration, and that's going to equal x squared. You take the square root of that number, that's the hydroxide. Don't forget, if it's a base, it's a hydroxide. Then you go 14 plus the log of the hydroxide to get the pH.